Magnets. What's up with them? Why are some things like your refrigerator magnetic, while other things like cutting boards are not? And it's not even the difference between metals and nonmetals, like conductors and insulators for electricity. It's really a difference in material. For example, these two metals here, an aluminum tent peg and an iron nail, behave differently. One is attracted to these magnets and the other one's not. What's going on there? So we're going to be exploring what magnetism is, where it comes from, what effects it has, and how we can actually control it. All right, let's get in. So we know that there is a thing called magnetism. It's been known for thousands of years. There's a story that goes that the ancient Chinese, about 2500 BC, I think, a general used a lodestone, which is a natural magnetic mineral, hanging on a string to navigate his way across a foggy field. And that's because the Earth has this giant magnetic field around it. The Earth essentially is a giant magnet. And we can tell that by using something called a compass. Now, a compass has a needle which is magnetic. And since the magnetic field around the Earth is always aligned in one direction, usually going basically from South Pole up to the North Pole, then what happens is the compass needle aligns itself with that same direction, always showing the direction of north. If you know the direction of north, then you know the direction of east, west, and south. So it's nice and easy. No matter where I hold this compass, it's always going to be pointing the same direction. And in fact, if I have a magnet on a string, it'll actually align itself in that same direction, pointing north. That's how I know what end of this magnet is north, and I colored it red here, and the other end I colored blue to indicate south. So that's how I know which end is direction is north and south. Now, magnetism and electricity are related to each other in a lot of ways. They both exist in fields. They both apply forces that are kind of like opposites attract and likes repel, only in the case not positive and negative, but north and south, for example. And they are a natural phenomenon. It caused, actually, magnetism, it turns out, is caused by the motion of electrons themselves in atoms for permanent magnets like these, and also, as we'll find out, through wires creating what we call electromagnets. All right, we'll get there in a moment. But for permanent magnets, one of the things to know is that you can never have a north or a south pole by itself. So positive and negative charges can exist alone. You can have a proton or an electron. It's possible. And you can have an object that has an overall net negative charge or an overall net positive charge. That's possible. But you can't have an object that has an overall net north pole. That doesn't happen. If I were to take a magnet and cut it in half, I don't end up with two poles, a north and a south. I end up with two whole magnets, a north and a south, on each one. So if I were to push these two together, they repel, showing that I have two north poles. And if I were to flip one around and pull it close, then I find out that it sticks. I have a north and a south. So I've got two complete magnets. That was fun. On each magnet that I cut. So cutting a magnet in half creates two smaller magnets. Now, magnets and the magnetic fields they create can apply forces. And just like we have electric fields and gravitational fields, we have magnetic fields, which are imaginary lines we use to describe the effect on nearby magnets caused by other magnets, or as we'll find out, electric current. So for permanent magnets, we describe the direction of the magnetic field as the direction that the north pole of a magnet wants to go or is pushed. So that means that magnetic fields go out of north poles and into south poles, because the north pole of a magnet is attracted to the south pole of another magnet, so it's pulled in. But it's repelled from the north pole of other magnets. So that means we have north into south. And since every magnet always exists as a pair of north and south, we always have what are called dipole field lines, similar to a positive and negative dipole for electricity. We have electric field lines that are coming out of the positive and into the negative. Here we have magnetic field lines coming out of the north and going into the south, looping around. If I hold two magnets nearby, the north and the south near each other, then I would have magnetic field lines that are coming out of the north and going into the south. All right, now let's take a look at this compass. This compass points in the direction of the North Pole, but look at what side is attracted to the South Pole of this magnet. It's the North Pole of the compass. That means that since the magnetic field lines run from the southern hemisphere to the northern hemisphere, they're going from a north magnetic pole to a south magnetic pole, which means that the Earth is not North Pole in the north magnetic pole in the northern hemisphere. It's actually flipped upside down. What's in the northern hemisphere up north of Canada is actually a south magnetic pole. And what's down south in near Antarctica is actually a north magnetic pole. We describe the direction of north and south not by what we call for the magnets, but by what direction the north pole of a magnet points. That's why we call it north, or why we call this the north pole of a magnet, of a compass. So the north magnetic pole, or the one that's actually in the northern hemisphere, is really a south magnetic pole. Fun fact. All right, now, these magnetic fields can apply forces to other magnets. If the field is uniform, then what we're going to have is we're going to have a torque on a magnet, because the uniform field will push on the north and pull on the south equally and oppositely and just cause a rotation. However, if the field is not uniform, then the north pole or the south pole can be affected more strongly than the other. And so what we get is we get a net force. One attraction is greater than the other repulsion, and so we can get a net force. Notice that I can pick up a nail. I can cause it to accelerate. The field around a single magnet like this is not uniform. It spreads out. And so it's strongest closest to the magnet and weakest when it gets further away, just like the electric field around charges. But in the Earth's magnetic field, which is roughly uniform, the magnetic needle here is not ripped out of my hands and flung north. It's just rotated. So if I have this, it just will rotate so that it will attract toward the northern hemisphere, right? Toward the North Pole, which is roughly that direction. All right, now let's talk about electromagnetism for a little bit, because permanent magnets, they're all well and good, but they're hard to control and you can't turn them off, right? But in about 1820, a man named Hans Christian, not Andersen, but Hans Christian Ørsted, who was a Danish physicist, he was a lecturer, he was teaching, and he noticed that in class one day during a lecture that a current that was running through a wire from a battery was causing a compass needle to deflect away from true north. I don't know why he had a wire and a compass on the table at the same time. Not sure what the experiment was. But you notice here, if I put this compass underneath this wire, it points in the direction of north, as we'd expect. But as soon as I run a current through this wire, notice that, whoa, it jumps. It points in a completely different direction. It actually points in a direction that's perpendicular to the wire, always. And if I lift this up, if I lift this up and place it on the other side of the wire, I notice that it actually points in the other direction. So it's one direction when below the wire and a different direction while above. And that gave Ørsted an idea. He did some experimentation, and he found out, I have here a setup of something similar to what he must have done. Instead of a battery, I have a power supply. Switch to turn the circuit on and off. And this wire runs through this vertical wire. So I'll have current running up along this cable, this wire right here, and then back along through my ammeter back to my power supply. But notice that what happened, if I place this compass near this wire here and I turn the circuit on, what I get is a magnetic field that is running perpendicular to this wire, and always perpendicular, and it seems to be going around and around in a circle. And so this is what Ørsted noticed, and he wrote up his conclusions and was given a bunch of prize money and things like that because he's genius. He noticed that a current going through a wire will create a magnetic field that is circular around that wire. And the direction of the magnetic field is given by something called the right hand rule. So you'll need your right hands for this. All right, now let's pretend that this nail is my electric current and it's pointing in one direction. So this electric current is going in this direction along the nail, pointing in the direction of the nail, so pointy bits, and then coming from that direction. So going in and then coming back out. If you were to take your right hand, and specifically your right thumb, and you place it in the same direction as the electric current is flowing, then your fingers will naturally wrap around the wire in the same direction as the magnetic field. You get that? So you can try this with a Sharpie if you want. So, or pen or pencil or stick or anything. Just take it, put your thumb around it, okay, and then your fingers curl naturally in the direction of the magnetic field. If the current is going the opposite direction, then your fingers curl the opposite. So essentially, if you have a current coming toward you, then the magnetic field is going to be anti-clockwise or counterclockwise going around. And if you have a current that's going away from you, then the magnetic field is going to be looking clockwise around that current. And it's in a circle going all the way around. Now, it's strongest when it's closest in and weakest as it gets further away, a relationship we'll look into later. But that is a fascinating idea. And it turns out that we're not done yet, because other physicists came along and they said, well, what if instead of having a long wire, what if you coiled it? Then the current at any point, right, would be going around in a loop, but notice that my fingers are always pointing through this coil of wire, always pointing through this loop, pointing toward me, away from you, if I have current going in one side and out the other. So I would actually be able to enhance or strengthen the magnetic field on the inside because I've got contributions from every little piece of wire going all the way through here. I get to amplify, to increase the strength of that magnetic field. And it turns out if we take it a step further and add more loops, it gets even stronger. And then we get to the idea of something called a solenoid. Now, a solenoid is a device that's designed to create inside of it a very uniform magnetic field. Just like two parallel plates will create a very uniform electric field, we can create a very uniform and controllable magnetic field with a solenoid, which is essentially just a tube that has a lot of coils wrapped around it. And so current will flow in and around these coils. Each one of those coils creates a magnetic field going around it. In fact, this one, we can say that the magnetic field will be produced this way if we have current coming in on this peg, going around and around and around, because any one of these coils, we see the right-hand rule tells us that the magnetic field is going to be going up along through the center here. And all those contribute to create a very strong and uniform magnetic field on the inside, and very weak and almost zero magnetic field on the outside. It's a very interesting device and very useful for studying magnetism. Right. So we have set up the idea that magnetism comes in two forms. Permanent magnets, which there's a video from Veritasium and Minute Physics that I'll link to that tells you exactly why some things are magnetic and some things are not. It's brilliant. And then there's also this form of electromagnetism, which is controllable and comes from the creation of electric current in a wire. And it turns out that that will create its own magnetic field as well. All right, we'll get into the mathematics of this a little bit later on, but for now, that's a good enough introduction for us. Great. Thanks for learning with me.